Something else that we're interested in are proper colorings of graphs. So if I give you a graph and some crayons and tell you to color it properly, then that just means color all the dots, but if two dots are connected, they have to be different colors. That's all that means. Now, Richard Stanley defined this thing that he called a chromatic symmetric function, or the CSF for short. And all that does is it records the possible proper colorings of a graph. So, for example, if we have a graph on three vertices like this, and x1, 2, and 3 just represent red, blue, and green respectively, then the chromatic symmetric function is going to look something like this. And there's extra terms in there as well, because those aren't the only three ways to do that. All right, so the chromatic symmetric function has this property of being a symmetric function, that's the name. And a function is symmetric if you can permute the variables and get the same output once you compute the function. So I have here an example and a non-example. Notice on the top line, if you commute x1 and x2, you get the same output. But on the second line, when you commute them, you don't get the same output for all x. So the second line is not symmetric. Symmetric functions, the set of all of those forms a vector space. And that means we can write the chromatic symmetric function in any basis that we want to, which is helpful. The classical way to write this is with the power sum basis. And Stanley used that to write an algorithm for computing the chromatic symmetric function efficiently and quickly. And he was playing around with that and specifically looking at tree graphs, which look like this. And he noticed some patterns, and so he gave this conjecture. He asked, if you have two distinct trees, will they have distinct chromatic symmetric functions? So can you distinguish trees based on their CSF? And a lot of research has been done on various subsets of this. Some things have been proven and disproven on subsets, but the problem itself, the conjecture, remains open. So we want a different perspective on this. And since we can write the CSF in any basis that we want to, we're going to use something called a star basis, which I'll define in a second. But for that, we need to define what star graphs are. So a star graph looks like this. You have some central vertex, and then you have the points that kind of make the points of the star. And we're going to label these with ST for star, and then the subscript is just the number of vertices in the star graph. All right, don't worry about the specific notation for basis. The important thing here is if you have a grouping of stars, so here we have a 5 and a 2, the chromatic symmetric function for that grouping is the product of the individual chromatic symmetric functions. And we'll write those also with ST5. The script should be different, I just can't write that fancy script in my own handwriting. So from here on out, ST, chromatic symmetric function. All right, so when we have a graph and we have this basis that we've found, but how do we get our hands on these stars that we're going to make the basis out of? We do that with something called the deletion near contraction relations, or DNC relations. And these are operations that we can do on edges of the graph. So the first one of those is deletion. You want to delete an edge, you just erase it off of the graph. The next one is dot contraction, so this one's a little bit more complicated. You take the vertices on each side of the edge, collapse them into themselves, so that's where this teal color came from, is the blue and the green collapsed. But you want to retain the vertices that you started with, so we have to pop an extra vertex up here, and that's your dot contraction. Leaf contraction works the exact same way, but after you get your vertex up, then you connect it to those collapsed vertices with an edge. And these four came up with a way to write the chromatic symmetric function in terms of these operations, or in terms of the graphs that are obtained through these operations. And so we add together all of the graphs that are with deletions, subtract out the dot contractions, and then add back in the contractions. So, quick example of that, this is the graph I start with. I'm going to do each one of those operations from my original graph. So there's our deletion, dot contraction, and leaf contraction. Now something important to note here, we're allowed to do those operations on any edge that we want to, but for the purposes of my research, we're just doing this on internal edges. So that's an edge that it's holding hands with edges on both sides of it. And once we don't have any more internal edges, so here these two are both external, these are all external, we're going to box it because we're not going to break it down any further with these operations. But over here, we still have this internal edge, we're going to repeat the process another time. Then when we write the chromatic symmetric function down, we'll just count up the partitions, so these pieces we'll call a partition, count up like partitions, and that'll give us these coefficients of each term. So there's two of those are positive because that was a leaf contraction. Subtract out the dot contractions, add in the deletions, and that gives us our chromatic symmetric function. Now, for the purposes of my research, I'm going to focus on a specific type of partition. So I said all of the pieces are called partitions. I'm just focusing on a specific kind, which is called a hook partition. That just looks like some number that's bigger than 1, followed by 0 or a bunch of 1s. So for example, a lot going on here, but just focus on this 3, 1, that would be a hook partition. The 4, 1 would be a hook partition. 3, 3, 1, 1, anything with just a string of ones after it. This also shows you, I computed all these by hand, they got very big very quickly. So that's a reason that we would want to look at the CSF for things, is to do this without having to do it by hand. All right, and then the graphs that I'm looking at, before I get into this, Dr. Myers in her talk talked about perfectionism and how her little word moved around. You're gonna notice my graphs doing this a little bit, so please excuse that. So the graphs that we're going to be doing this on are called Plankton graphs. And we're gonna construct these by starting with a path and then sticking some cycles into it. And you can use any size cycles that you want to as long as they're consistent throughout your graph. And the rule is you connect the cycles to the graph or to the path by their vertices. And you can put multiple cycles on the same one, you just can't glue the edges together. So that makes a Plankton graph. And you're gonna want to keep track of certain things about this Plankton graph. You're gonna want the path length, the number of cycles that you're using, the number of internal edges. So note this one here is the only external edge because it's not holding hands on the other side. You're also going to want the number of vertices. If you have a graph constructed like this is the general theorem for any size cycle, so that we have an example of 3. Any size cycle you want to, this formula will give you the coefficient, so the 2 and the 1 we saw earlier, the coefficient of these certain types of partitions. Looks a little bit complicated. I'm going to walk you through how I did it using the 3-cycle examples, so you can kind of see where I came from. When I was working with this to begin with, I used certain letters. The specific ones don't really matter. To use certain letters to keep track of the operation that I did, so the deletion, dot contraction, lead contraction. And this was just so I could visualize what I was doing. And notice that since we're doing these operations on internal edges, the word length is going to correspond to the number of internal edges we have. And I noticed as I was doing this that there were certain patterns that kept popping up in certain specific places in the word that happened to correspond to where the cycles were popping up. And so from there, I started building the formula. So in the partition, if we have like 3, 1, 1, for example, the only way we can get those ones to appear is doing a dot contraction, because that gives us that single vertex that we didn't connect back. So we know that we have a certain number of these ones in the partition. Those can only be gotten through those dot contractions. So -1 to the j gives us that term. That pattern that I saw with the letters, there were 2 ways that each of the 3-cycle words could be spelled, and so that gave me a 2 to the n. And then since we know how many dot contractions we have to do, the j, we can find the number of spots that are left over for us to do those in. And from here, I thought I was done, but I had an issue. Because remember, we're doing this on internal edges, but if we don't have the ends capped off, or if we do, that can make an edge that was external now internal. And so I had to introduce, you can barely see it, I had to introduce this delta term to account for that. And that did actually finish my formula. So this is the same one again, just in the phrasing for the 3-cycle case that my mentor and I proved last year actually. We also found this corollary from it. So we're interested in looking at structural properties of these graphs. And if you're given your formula, but you don't know what the graph looks like, you can actually find the number of 3 cycles by just setting j equal to 0. And that will make everything else fall out. You'll get 2 to the m, and then you can retrieve the 3 cycles from that. And so some future work that I would like to get into includes finding other similar formulas for other types of partitions instead of just hook partitions. I also want to explore what happens if you have cycles of different sizes within the same graph. So I said we can use any size, but it has to be consistent. What happens if it's not consistent? And also the more structural properties. This is really what I want to go for long term, because that's going to help us potentially make progress on Stanley's conjecture. And then I would like to give a special thanks to my mentor, Dr. Lawson, who was supposed to be in the room, but he had to monitor another talk today. Thank you all.
Questions? I'll ask a question. Can you tell me more about a Plankton graph?
Plankton graph,
how does
yes.
it have to be a triangle that you attach, or can it be?
So that's what the cycle size is. So you can do, let me see. Okay. So these don't have to just be the triangles. If you have like a 4-cycle, for instance, is there a marker? If you had a 4-cycle, that would look like a square, I presume, if it attached on there, or a 5-cycle. Any of those, When you increase the size of the cycle, you get something the size of a triangle. So it does not happen to switch branches.
But it's all the same, like if you're.
With my current research.
With your
it's all the
definition,
same.
like, yeah.
I got some markers. Do you need some markers?
Markers, perfect,
Let me-
yes.
I'll
Let me
walk them up
just-
there as opposed to.
I'll draw an example for you.
3 different colors, just matters.
Alright, so if I have I'll turn this around and just. Alright. That's obviously not a square, but if you had cycles, so that would be a 4 cycle or a 5 cycle, you could extrapolate.
Is that still a Plankton graph?
Yes.
And where did you come up with the name or hear the name Plankton graph?
Fantastic question. So as I was building these, Dr. Lawson asked me, he was like, well, like, since you kind of like came up with the family of graphs, more or less, like, what do you want to call it? And I was like, I don't know, like, I don't want to call it just, my name graph. I was like, that feels a little weird. And so I was looking at it and I was trying to figure out if it looked like something. And I was reminded of like a little like fish or plankton with like little flippers, because that's what the 3 cycles specifically reminded me of. So I called it that instead.
What letters would this correspond to? Or-
Would this correspond
Yeah.
to? It depends on what operation you do. So with the letters that I had, L, M, and R, L is for the deletion, M was the dot contraction, and R was the leaf contraction. That is because when you're doing your graph, typically, our graph here, the leftmost operation, just in order, is the deletion, and the middle one and the right-hand one. That's where those came from.
So the words actually are the path from the Plankton graph to the kind of graph you're trying to come.
Yes, so when I had, let me see if I can get back to it really quick. So, if I have this means that I did a deletion. The X actually means that the previous operation made the next edge external. So an X means no operation can be done. So this, I did deletion, couldn't do an operation, did a leaf contraction, a dot contraction, and 2 deletions, and then was finished with my graph. So your graph is the path from the graph to the hook partition.
Thank you. Let's thank our speaker one more time.